we can look closely at gases and solutions from the physical part, having understood the physical part, so that we can look at them in a more chemical part as we move forward. So that's the next thing we're going to get into now, right? So that thing, yeah, PV equals nRT. Then becomes important here. Yeah, one? Because we talk about standard temperature and pressure. Standard temperature and pressure. Ne? And that's where, if we know that the pressure in the atmosphere is 101,300 Pascal for 1 mole, with a gas constant of 8.314 J/K mole, and temperature is 273 0 degrees Kelvin, then this gives us a volume of 22.4 liters. All right, so this literally goes into depth. Those calculations, and remember, I always keep saying, in grade 10, we introduced the concept in a very gentle manner, just so we're excited by it. But in grade 11, we go a little bit deeper into it. Like, who's that pastor who likes to say go deeper? We go like that, see? Then, yeah. So that means for 1 mole of gas, 1 mole having the same number of particles expressed by Avogadro's number. And Avogadro's law is that for different sizes of volume, the number of particles are the same regardless of the chemical that we're looking at. It can be ammonia gas, it can be chlorine gas, it can be oxygen, it can be carbon dioxide, it can be nitrogen gas, it can be any gas you can think of, the noble gases or hydrogen. As long as you have 1 mole, you have 22.4 dm³ if it's exposed out in the air. And the volume of the gas changes in proportion to that number, 22.4 dm³. So that means if we have, like in here on page 291 for grade 11, if we have 2.3 moles of a gas, let's say it's hydrogen at standard temperature and pressure, and we must find the volume. Then we can say the volume of hydrogen gas equals 22.4 times 2.3, which is the number of moles, and we will end up with 0.52 dm³. And again, this also tells us that if we have a gas and another gas in a container, or they are reacting, then the stoichiometric coefficient of the first gas and the second gas divided times the second gas will give us the volume of the first gas. So in other words, on page 292, if we're given that hydrogen gas reacts with oxygen gas to give us water vapor. And we now look at the number of moles become important, these coefficients here, because they are stoichiometric coefficients. So if they say 3 dm cubed of oxygen reacts with a certain amount of hydrogen, so we must find out how much water is produced. Find out volume of H2O. So we will say the volume of H2O then becomes the stoichiometric coefficient of that H2O is 2, and the stoichiometric coefficient of oxygen is 1, and the volume of oxygen that's given is 3 dm cubed. So then that means 6 liters of water would be produced. So that's the long and short of it. So yeah, so in some cases, some gases do react, and when they do react, then we need to account for what volumes go in and out of the reaction. So we've just done that with that. And again, it sounds like repetition because the whole week we did it, but from a grade 10 perspective. But now we're going at it after understanding some of the gas laws that are important and do give us an indication of what really goes on when we think about this from understanding the physical part of putting gases in containers. Now we don't only put them in containers, we're also having them react with each other. The other example is that of burning is it propane. So we've done it, but again, just as a reminder, on the same example, it's page 292 in grade 11. We have propane, which is a gas. It's burned. So when we combust or burn something, we burn it in oxygen. If we chair or la paraffin, la glass. If we ka letswalla ka godimo le a tima sa lo a bona a zango wa bona nto ga o tswalla that glass thing o e tswalla ka godimo a zango wa e dira. Okay, maybe I wouldn't advise you try it, but if you're daring, o e tswalle ka something o to bona mara e tlo tima because, or maybe let me not make that example. Okay, Bryce teno salwa bone e ba le mashuba ka mofase, ba direla mashuba ka mofase. Azango bona di Bryce teno tse batho ba di tielang tsona gae. They usually have mashuba ka mofase. So if mashuba le wa tswalla, a gona moyo tsenang. So because a gona moyo tsenang, then there won't be combustion. So the reason why le mashuba out is because moya tshwantse tsene so that the oxygen can help burn the coal or the wood that you're burning. The same thing is what you see here. So masuba is for the oxygen, because oxygen is what allows us to burn things. But if we tima oxygen in fish, then we tima mullo. So now we're given this equation where we are burning a hydrocarbon, a gas propane, which is, I guess, it's flammable. And then it gives us carbon dioxide, which is a greenhouse gas, and water vapor, which is also a greenhouse gas. Right. And this is at STP, at standard temperature and pressure. So we are going to burn the volume of propane is 3.3 dm cubed. And we must find out the volume oxygen that is needed. So from our reaction, the stoichiometric coefficient for propane is 1, for oxygen is 5. Ne? And we must work out the volume of oxygen using those stoichiometric coefficients. So again, VA equals A over B times VB. B are the oxygen, A are the propane. So VA, but this one will just say it's VB, and we don't know it. So stoichiometric coefficient for the first gas, K1, and the stoichiometric coefficient for the second gas, K. Sorry, this is VB, and this is VA. And stoichiometric coefficient for VA is 5, and then for VB is 1. Yes. So that means the volume of oxygen, 1 or 5 rather, over 1 times 3.3. And this is going to give us 16.5 dm cubed. So you'll be surprised. The same example is the one that we were doing in grade 10 textbook. That one? Yeah. And again, the same calculations, they bring us back to solutions. Right. And again, they remind us that we use the calculation here, concentration equals number of moles divided by volume. And the molar concentration of a solution is the number of moles of solute per liter of solvent, right? And it's more commonly given as moles of solute per cubic decimeter of solution. So to calculate the concentration, we use this formula. C equals N divided by V. And that gives us the molar concentration, right? This is calculated in mole per dm cubed, or mole per liter, or let's make it an L like this, a square L. Yeah. So this is molar concentration. And now this concentration, why wanna rate and extent of chemical reactions jamo grade 10. Why one? So this means if we're given, no, sorry, I didn't mean to, yeah. So on page 294, for our grade 11 book, if we are given sodium chloride, so now the concentration works the same whether it's for gas or for substance that you dissolve in water. The concentration, we work it out the same. It's always going to be a molar concentration, and its number of moles per liter or moles per dm cube. So now we've got sodium chloride, which is given in grams, or rather, sodium chloride is given, and we must work out its molar concentration. We need a certain amount diona that we must work out so that we can prepare a 500 cubic centimeter volume of solution, 500 cubic centimeter volume of solution, standard solution that has a concentration of 0.01 moles per dm cubed. So the first thing we must do is convert the units, because units are in cubic centimeters. Did you get disconnect? Oh, askis. A network yarna sugocha. So we must take 500 cubic centimeters and divide it by 1000 so that we get dm cubed. So if the concentration is 0.01, so we know that the concentration is given as 0.01. So we must first find the number of moles, and then we'll be able to find the mass of the sodium chloride that we need. So we're gonna work in reverse using this information, then calculate the molar mass, then we can find the mass. So then the concentration will be 0.01 equals number of moles times volume, which is 0.5. Then the number of moles itoba 0.005 moles of sodium chloride. Right, now this information, where do we use it? We need to first remember the number of moles is the mass divided by the molar mass. So on our periodic table, we will find that the molar mass is 58 grams per mole. Therefore, the mass will be the molar mass times the number of moles. And this is going to be 58 grams per mole times 0.005 mole. And this is going to give us 0.29 grams. So we'll need a very small amount of sodium chloride to have a concentration of 0.01 moles per liter. So it's literally not even 1 gram. 1 gram is too small. It's too small. So I'd like us to stop here so that when we continue on Tuesday, with titration. Titration is simply a technique where we determine the concentration of a solution that we don't know. And they can be used in different types of reactions, including acid-base reactions and reduction-oxidation reactions. So titrations we can also revisit from grade 10, just a little bit. And then we will build on them like that. So before I conclude, do we have questions? Amos? I'm not put you. Oh no, get a Tuesday because Tuesday is for science, but Monday we have maths class, I get. Yes, so Monday we have class for maths, Tuesday we have class for science, Wednesday are in a class, Thursday another class for science, and then Friday another class for maths. And then Saturday we start with maths from 10 until 12, 1 hour break, and then science from 1 until 3. I get.